Um, so then we have di squared is di squared minus IE di AI plus AI di plus a squared, which will drop. With these a's, this thing commutes. So D1 acting on A1, there's no x dependence. So keeping the order consistent, it doesn't make any difference with this B field. So this is di squared minus 2IEB over 2 times x dy minus y d by dx, which this is our cross P equals L. Okay, up to factors of I. Okay, so the more interesting thing for us is the spin part. Sigma ij is epsilon ij k sigma k sigma k. Should work out what that is, which is epsilon ij k times 2s k. So that sigma 1 2 f12 plus sigma 2 1 f21 is 2 times 2s dot b. So 4s dot b. And when I get back to go back to our original d squared, which had that piece there, I just write out, I get d0 squared plus m squared minus del squared minus eb, and I get L from the derivative squared, and I get I have an e over 2 there, so one of the 2's gets out of there, becomes L plus 2s. Okay, and then at this stage we've got the L plus 2s. This gives us the G factor, and you put this into the usual Schrödinger equation by doing the usual non-relativistic reduction, right? So there's, I think, the cleanest calculation of the L plus 2s factor that we get. Okay, that's not how we'll do the calculation of G minus 2 though, so let's set up the G minus 2 piece. First in the setup is the Gordon decomposition, which I mentioned last semester, but let's say it again. Okay, I'm going to quickly derive it. If I take u bar of p prime, gamma mu u of p, I can write that as u bar of p prime p slash prime gamma mu plus gamma mu p slash over 2m okay. Basically p slash equals m, p prime slash hitting that guy equals m, and okay. We then let P slash equals 1/2 p plus p prime slash minus 1/2 p prime minus p slash, likewise p prime, with a plus sign there. The first term turns into, you then get the first part goes to, let me just call it capital P, gamma mu plus gamma mu P, which is the commutator. I then get the other one gets the anti-commutator. If this is Q, I end up with Q slash gamma mu minus gamma mu Q slash. So that turns into the sum and difference. We end up with U bar P prime gamma mu U of P is U bar P prime P plus P prime mu over 2m plus I sigma mu nu Q nu over 2m U of P. Okay. So that's the Gordon decomposition. And this piece looks like the convection current. Which is just like a scalar. So the L dot B piece would be live in there. This is the spin piece. That's special to fermions. And then let me very quickly show you how G minus 2, G is equal to 2 lives there. Okay. This is the derivation I did really quickly last semester, but let's just go through it again. If we have the Hamiltonian is minus mu dot B for a magnetic field, that's G over 2 E over 2m sigma dot B, because S is sigma over 2. So I've used that. And the magnetic moment is G E over 2m F. Okay. Then sigma dot B goes through the steps we just did. It looks like U bar over 2 sigma mu nu, sigma ij, U Fij, that's what we just did. That goes relativistically to U bar sigma mu nu, U, there's the 1/2, F mu nu. So the Hamiltonian is G over 2 E over 2m U bar sigma mu nu, let's make it psi bar sigma mu nu psi F mu nu over 2. Okay. If we take matrix elements, the matrix element then of H magnetism is G over 2, E over 2m, U bar sigma mu nu, U. This becomes Q mu, or epsilon nu. And there's a factor of 2 there. So let's see if I get all my factors right. Yes, so that's just then U bar G and let's see, how many factors of 2 do I have? I'm missing, I hate to blow this factor of 2. It's the factor of 2. 2, 2, 2, G over 2. Oh, there was a 1, that's the factor of 2 I'm missing, over 2. Right, I had a F mu nu over 2. Becomes G over 2, E over 2m, sigma mu nu, Q nu, U times the external field, epsilon. So that our usual current with the gamma mu gives you G is equal to 2 for the spin factor. Okay, so so there's 2 quickie derivations. I wanted to use we're going to use a general form for the matrix element. Okay, so the matrix element of a current will be mu is going to have this following form. U bar P prime gamma mu times F1 of Q squared plus I over 2m F2 of Q squared sigma mu nu Q nu U of P. Okay. Now, how many people want to see the derivation? I have the derivation sitting here. It's easy to do. But I don't know if you've seen it before, if we're wasting time by redoing it. So somebody has to speak up and say they want it. You want it? Somebody? All right, somebody wants it. All right, good. So, I mean, here's basically the issue. This is the most general one, consistent with Lorentz invariance. I'll use parity, though I'm not going to talk too much about it, and gauge invariance. Okay. If you wanted to start off without assuming those, well, let's first just do Lorentz and parity. Okay, so in general, mu could have various forms. U bar of P prime, well, it could have gamma mu. Gamma mu is obvious. It has to be a vector, so it could have P plus P prime mu, or it could have P minus P prime. Let's call it Q mu, which is, I'm going to use Q mu as P prime minus P. So if you have those guys, it could it certainly could have sigma mu nu q nu. It could have sigma sigma mu nu p nu. So that's p plus p prime. Okay. There's actually nothing else consistent with parity, and as I said, I won't do too much parity, but parity would always just bring in a gamma 5. But those are the only vectors that we have, 4 vectors we have at our disposal. We have the sigmas, so we have one index left over there, and all these guys. B can be gotten rid of by Gordon decomposition. That goes into A and E, so you can get rid of that guy. If I use gauge invariance, Q mu mu is U bar P prime. Well, the A term gives 0. The B term gives 0. The C term gives C Q squared. The D term gives D times 0 because it's anti-symmetric. And the E term gives sigma mu nu Q mu P nu. Okay. There's no way for these two guys to cancel each other. You can just see this by taking Q in random directions. Sigma varies all over the place. Q squared stays the same if you choose it right. Okay, so that says that C has to be equal to 0, D has to be equal to 0, and I'm left with the two that I chose there. Well, one could have chosen A and B and gotten rid of D, but the convention is to do the one we have. So there's the general matrix element. However, for the calculation I'm going to do, so this is the conventional one. And actually we can see from what we did before that the magnetic moment by using the Gordon decomposition is E over 2m F1 plus F2, and at low energies we're going to take these to be at Q squared equals to 0. So F1 of 0, F2 of 0. But F1 of 0 is equal to 1 by charge that's, since this is the electromagnetic current, and we normalize this to have the electromagnetic current be minus E times the charge. That doesn't get renormalized by which is one of our Ward identities. So this is E over 2m 1 plus F2. And for the calculation that we're doing now, we just basically do G minus 2 is F2 of 0. Okay, so that's what our goal is, to calculate F2 at Q squared equals to 0. Okay, so I've rushed through that, I felt, but if you have questions, you have to ask. Okay. If not, we'll just start the calculation. Okay. We're going to calculate the vertex correction. Looks like this. Momentum P coming in, P prime going out. Label the photon momentum by K. Actually, I'm going to reverse that. Let's reverse it. It saves a lot of minus signs. I reverse. We integrate over. It doesn't matter. So this is P plus K. And this one is P prime plus K. Okay. The vertex minus IE, I call the vertex here, I'm calling it gamma mu, is integral d4k 2 pi to the fourth. On this side, right over there, I have minus IE gamma alpha. I then hit the propagator I over P prime slash plus K slash minus M. I come along, I hit minus IE gamma mu. Next propagator is I over P slash plus K slash minus M. And at the end I hit minus IE gamma alpha again. Okay. When we rationalize that, the numerator is gamma alpha P slash prime plus K slash plus M, gamma mu P slash plus K slash plus M, gamma alpha. The denominator is, okay, anyone see my mistake? I have a mistake up there. Feynman rules. I have a minus I over K squared missing from the photon propagator. Okay. Good. Okay. We have the denominator is K squared times P plus K squared minus M squared times P prime plus K squared minus M squared. Okay. The goal, the best way to do this is to use the Gordon decomposition. Okay. What we're going to do is we're going to rewrite the general matrix element it's U bar of P prime. We're going to use it in reverse. I'm going to get rid of sigma mu nu. Sigma mu nus are tough. You don't like to have to find so many gamma matrices. So I'll write it in terms of gamma mu f1 of q squared plus f2 of q squared, and then minus 1 over 2m p plus p prime mu f2. So I'm going to u of p. Okay, so I wanted to get rid of sigma mu nu, And now I'm going to reduce every term to either gamma mu or p plus p prime. So reduce everything. Gamma mu or p plus p prime. And the one we want is the p plus p prime, so we're going to drop all the gammas. Okay, that makes life a lot simpler. So there's either one gamma matrix or none, and we can throw away all the ones. Okay, so here follows a bunch of explorations of this. I take this apart, first looking at the terms that are in m squared, then looking at the terms that are in m, so the cross terms with the p's and the k's, and then looking at the others. Okay, but first, the typical trick, the place you start is you do the Feynman parameterization. So 1 over d. All right, so I'm going to use, let's show you what I use first. 1 over ABC is 2 integral 0 to 1, 0 to 1, 0 to 1, d alpha, d beta, d gamma, delta 1 minus alpha minus beta minus gamma of A alpha plus B beta plus C gamma cubed. So that's this Feynman identity. We'll quickly do the delta function, so this becomes 2 integral d alpha d beta one over this thing cubed still. When doing the delta function just forces the integral. So as long as alpha plus beta sum to less than 1, then this delta function can be satisfied, and you can do that. So we have to keep alpha plus beta less than 1, so the region here, if this is alpha beta parameter space, is that triangle there, 1 to 1. So we integrate over the triangle, which is alpha plus beta is less than 1. Or the way I'll actually do the integral when I get to it, I'll do the integral d alpha d beta. I do the integral beta 0 to 1 minus alpha, and then I do the integral alpha 0 to 1. That's what I'll end up doing, but you could of course reverse that. It's symmetric. And let's point that out because I'm going to use that. Okay. If I do use this, then 1 over the denominator is 2 integral d alpha d beta over this triangle of 1 over something cubed with this script d is alpha p prime plus k squared plus minus m squared plus beta p plus k squared minus m squared plus gamma k squared. Okay, that can be simplified. We'll use p prime plus k squared minus m squared is k squared plus 2p prime dot k. Okay, because p prime squared equals m squared. Likewise for the other one, plus 2p dot k. And then what I will also need in just a second, so let's work it here on doing kinematics, is p prime equals p plus q squared. So since that's true to the first power, let's square it. P prime squared is p plus q squared, which is on one side is m squared, the other side is m squared plus 2p dot q plus q squared. Applies 2p dot q equals minus q squared. Likewise, 2p prime dot q turns into plus q squared. We're going to end up dropping all q squareds. But then the piece that I need to use is p dot p prime is p plus q dotted into p is m squared plus p dot q, m squared plus minus q squared over 2, which we're going to end up dropping. Okay. So there's a bunch of kinematics. Those are pretty standard. But basically, whenever you get this, anytime you see p dot q, you turn it into q squareds. So everything becomes a function of q squared. Okay. But then if I use this, d is, well, each of these terms gets a k squared. There's a k squared there, a k squared there. The alpha plus beta plus gamma is 1. So it starts off with k squared. The next term is then plus 2k dot alpha p prime plus beta p. And that's it. Standard next trick is we shift. I take k plus alpha p prime plus beta p mu, call that L mu, then d becomes L squared. So L squared takes care of that term, the next term, and then you get an extra square, so you have to subtract off the square. Becomes minus alpha p prime plus beta p squared. Which is L squared minus alpha squared m squared plus beta squared m squared plus 2 alpha beta turns into m squared also, because p dot p prime is m squared plus q squared, so I call that m squared plus order q squared alpha plus beta squared m squared. Okay, good. I will use that this is symmetric in alpha beta in just a minute, so let's point it out. All right. So we've done the shift, we've got the denominator in terms of L. We have n mu. Okay, so we just have to shift. In the numerator, we take k slash, write it as L slash minus alpha p plus p prime, etc. N mu, the shifted n mu is gamma mu L slash, let me call it capital P prime slash plus m gamma mu. That's first one was gamma alpha, the middle one's gamma mu L slash plus capital P gamma alpha, and the P mu was 1 minus beta P mu minus alpha P prime mu, and P prime mu was 1 minus alpha P prime mu minus beta P mu. Okay. So our goal now, there'll be a series of steps where we take this and reduce it to gamma mu's or p plus p prime mu's. And so let's do that. So let's first look at the m squared terms. Now there's actually only one of them, so m, and that was a plus sign. I'll change it in just a second. That's a plus sign. I then end up with gamma alpha, gamma mu, gamma alpha is minus 2 gamma mu. That's one of these identities. So we drop it. Okay. 2, the m terms. Okay, we see m multiplying L p mu p prime slash there and L p there. The first things you do is anything that's linear in L, you drop, because the rest of the integration is symmetric in L, right? So we drop those guys. We're left with, we have m gamma alpha p slash prime gamma mu gamma alpha plus gamma alpha gamma mu p slash gamma alpha. We're going to use gamma alpha a slash b slash gamma alpha is for a dot b, one of these tricks. So this turns into, there's the 4 from the trick, becomes p prime mu plus p mu plug in what those are. It's 4m 1 minus 2 alpha p prime mu plus 1 minus 2 beta p mu. And then remember, the integration that we have is symmetric in alpha beta, so the integral of alpha and the integral of beta are the same thing. So we can write this in symmetric form as 1 minus alpha minus beta. It's the integral in alpha and the integral of beta are the same. 2 alpha is the same as alpha minus beta. P plus p prime mu, and that's one of the terms we want to keep. So that's one of the final answers. Okay. 3, m to the 0 terms. Okay, well, if we go back up here, we're going to dispose of them bit by bit. We'll first take, there's 3 terms. There's L times L, we're going to end up dropping that. There's L times P, that's odd in L, so we'll drop that. And there's P and P. So we can quickly get rid of these guys. Let's just see. The first one is gamma mu L slash gamma mu L slash gamma alpha with 2 L squareds. Here you can end up using, I mean, you see there's no p plus p prime there, but let's show you that it does reduce to gamma mu. Integral d for L mu, L nu, L squared minus a squared. Well, that's by Lorentz invariant is a quarter g mu nu, integral d for L squared over L squared minus a squared. This is to any powers. So basically, L mu L nu turns into g mu nu. So this guy turns into L squared over 4 gamma alpha, gamma beta, gamma mu, gamma beta, gamma alpha. This gives me minus 2 gamma mu. This gives me another minus 2 gamma mu. This becomes L squared over 4 times 4 gamma mu, which we drop. Okay. So it's true, everything has come down so far to either gamma mu's or p plus p primes. The second one here was we drop linear and L. By symmetry, gives no contribution. And the last term is gamma alpha p slash prime gamma mu p slash gamma alpha. Okay, that turns into minus 2 p slash gamma mu p slash prime using gamma alpha a slash b slash c slash gamma alpha equals minus 2 c slash b slash a slash. Okay, you just work a bunch of commutators and that falls out. Okay. These, if I have anything times p slash on u of p, that's going to take it into that thing times m u of p. And of course in the p slash and p slash prime we have some of those. Likewise on the other side. So the minus 2 p slash gamma mu p slash prime equals minus 2. It's 1 minus beta p slash, we can't get rid of that because it sits on the wrong side, minus alpha m gamma mu 1 minus alpha p slash prime minus beta m. So I've converted some of those into m's, but not the last ones. That's useful because it gets rid of, so again, we're going to have an m squared piece with the gamma mu that drops out. So we then have to work on this guy a little bit. This won't take too long. We're coming along fine. So the alpha beta m squared gamma mu we drop. We've got that in the right form. When I have gamma mu p slash prime, okay, we write that as gamma mu p slash prime minus p slash prime gamma mu which in the linear terms is going to drop out. I mean, let's see, we'll turn into then 2 p prime mu minus m gamma mu, which this guy will drop. And clearly the p primes are going to work out just fine. Likewise, if I have p slash gamma mu, the same trick turns into 2 p mu minus gamma mu p slash, which we're going to drop. And so the m to the 1 terms are, I have minus 2 there, there's going to be 2's there, and there's a minus sign here, minus alpha m times that, and beta m times that. So quickly collect those guys up. Is 4m alpha 1 minus alpha p prime mu plus beta 1 minus beta p mu. Okay, by symmetry, I can write this as 2m. I take alpha 1 minus alpha, I add it to beta 1 minus beta, so each of those two terms are the same. P plus p prime mu, and that's one of the terms I keep. All right, one more term to go. The third one in here, the m to the 0 term, is minus 2, 1 minus beta, 1 minus alpha, p slash gamma mu p slash prime. So the work is the same here. We take this guy, we write it as p slash 2p prime mu minus p slash gamma mu, which now that p is unobstructed over to the u bar that sits on the side. So that turns into m times 2p mu, 2p prime mu. The next term we write as minus p slash p prime slash minus p slash p prime. P prime sits on that side, gamma, and then close brackets, gamma mu there. That turns into 2p dot p prime. So that can be dropped because that's a gamma mu term. This guy here turns into m. This guy, we use the identity that we used up above. It's sitting right there. To write that as 2p mu. So this ends up, after this work, is just m times 2p plus p prime mu times this 1 minus beta, 1 minus alpha, and I have a minus 2 sitting times minus 2 from up above. All right, so at this stage we collect terms. That's all the terms. We've reduced everything to gamma mu's, or this would be the efficient way to calculate the gamma mu piece also. The numerator there's a lot of 2m p plus p prime mu's. In the order we found them, the first one was 2, 1 minus alpha minus beta. The second was alpha 1 minus alpha plus beta 1 minus beta. And this last was minus 2, 1 minus beta 1 minus alpha. Okay, if you add those all up, it's 2m p plus p prime mu turns into alpha plus beta 1 minus alpha minus beta. Okay, the overall factors of 2 there cancel, so there's no term without an alpha or a beta. That actually turns out to be important. If that didn't work, for time I'll show you that would have given an infrared divergence, but it doesn't happen, so it doesn't. Okay. At this stage, there's no L dependence here. I've gotten rid of all my L dependence, so I can do the scalar integral. I have the integral d4L over 2 pi to the 4th, 1 over L squared plus alpha plus beta squared m squared cubed. Well, it's nicely finite. It's minus I over 32 pi squared. Dimensionally, you know it has to go like alpha plus beta squared m squared, and all you have to do is get that 32 pi squared out of the thing. So there's no need to regularize, it's just nice finite integral. Okay, so it goes like L to the fourth over L to the sixth, so you have to get that factor. Okay, that's guaranteed. Such that minus IE gamma mu, well, I collected a minus 2e squared from before, the integral d alpha d beta over the triangle, minus I 32 pi squared over, let's see, 2m p plus p prime mu alpha plus beta 1 minus alpha minus beta alpha plus beta squared m squared. Okay, it's worth pointing out that that integral is finite, but let me just do the integral or give you the answer, and then we can come back and look at the integral. I get, the integral turns into, this first integral, the 1 turns into 1, the second integral turns into minus a half. You can see alpha plus beta, alpha plus beta, alpha plus beta all cancel. The integral d alpha, d beta over the triangle is a half. So I get a half out of that. I get e squared over 8 pi squared 1 over 2m p plus p prime mu, which, if I write it, is minus 1 over 2m p plus p prime mu times alpha over 2 pi. Okay. At that stage, we have our answer. F2 of 0 is alpha over 2 pi is g minus 2. Okay. The only thing I didn't, just so I did every single step of the thing, let me do the triangle integral, d alpha, d beta. There's actually some interesting stuff in this. The integral that we have to do is 1 over alpha plus beta. Okay, where you end up doing that, integral 0 to 1 d alpha, integral 0 to 1 minus alpha d beta, 1 over alpha plus beta, is integral 0 to 1 d alpha log of, it's the log of 1 over 1 minus alpha, upper integral alpha plus beta is 1, the lower is alpha. That integral is just 1. The other integral, as I said, was a half, so that gave me my factor of 2. Okay, so there's that whole calculation. Yeah, look, I have a page on what on the other terms, but maybe I shouldn't bother with it. But let me just say that one of the things that you can see would have happened. Let's imagine this didn't have alpha plus beta there. There was some constant piece there. Then you would end up having the integral of 1 over alpha plus beta squared. That integral, when you do the first integral, gives you the integral d alpha 1 over alpha. That diverges. Diverges at the lower end. The gamma mu pieces have that factor there. That turns into, that's the pieces that turn into infrared divergences. That the lower end of this integral is basically the fermion lines carrying very little momentum. So the divergence, if you didn't have that, and you can certainly go back, and it's easy to see that the m squared pieces, you know, if we go way back to the beginning here, the m squared piece wouldn't have that. We only had one m squared piece. It was m squared gamma mu. So that won't have it. And so there'll be infrared divergences in the other pieces, which are crucial for this understanding of, you know, that you have to cancel the infrared pieces divergences with Bremsstrahlung or diagrams. Okay, but this piece is nice and finite. It worked out perfectly. We get our answer. Okay, so I think I'll stop there, unless there's questions. You have questions? Yes?
So we kept the L squared term?
Yes.
That have an ultraviolet divergence?
Yes. Yes, so basically my next page here was going to sort of map out where the ultraviolet divergences come from. The main ultraviolet divergence comes from the L squared piece, because you see you have then L squared d4L over that denominator, which was to the L to the 6th. So that picks up the ultraviolet divergences. All the others go to infrared divergences. So that particular diagram has either infrared or ultraviolet divergences. All the others then have, in principle, IR divergences. Okay. And your choices there on the infrared divergences are either you can put in some cutoff like a fictitious photon mass, which you then set to 0 at the end, or you can do dimensional regularization in the infrared also. You can dimensional regularize both UV and the infrared. The dimensional regularization trick there is not as well known as putting a photon mass, because photon mass sits in all the textbooks. But it would have been in our book if we hadn't had space limitations. Gene worked out beta decay, gory detail, doing infrared doing dimensional regularization in the infrared. But I should have saved the chapter, the preliminary chapter. It was a great chapter, but it got thrown out. But it can be done. Okay, good. Okay, good.